Good morning to one and all present here. Today we are going to see about linear applications of op amps in LIC, which comes under unit 2. Particularly we are going to see in this session about integrator and differentiator. So what do you mean by an integrator and what do you mean by differentiator? First we will see about the integrator. So integrator is nothing but we can simply call in electronic circuit as low pass filter. That is, the voltage that is proportional to the running time integral of the input voltages. In a running time integral, the upper limit of the integration is t, and the gain is less than unity, the attenuation is more. For perfect integration, we have to give the input to the inverting input, whereas we will get the output as an inverted output with respect to input. So already I have said that there are two inputs for an op amp. One is inverting input and another one is non-inverting input. Depending upon the inputs given, we call the circuit as inverting input and non-inverting differentiator or integrator. So here I am using inverting integrator because I have given the input to the inverting input via R1, that I name it as V2, and V1 as non-inverting input, that is grounded. So the output is, we have to get, it is a combination of RF and CF. So RF is the resistor we are going to use in series with the input and the inverting input of an op amp, and CF is parallel with the op amp and in series with RF. So the CF is feedback used for the op amp. So output will be the integral of V input dt plus the capacitor voltage C. So 1 by R1 CF integral over 0 to t V input dt plus C, where C is the integration constant and it is proportional to the value of the output voltage V0 at time t equal to 0 seconds. Right. If we consider an example, let I give an input as square wave, the output will be a triangular wave because the input is given to the inverting input. Another one is, if I give the input to the sine wave, the output will be a cosine wave. Next one, when V equal to 0, the integrator works as an open loop amplifier. If there is no input, the output will have the capacitor CF acting as an open circuit, so it acts as an open loop amplifier. Right. The input offset voltage V input and part of the input current charging capacitor produce the error voltage at the time of the integrator. Therefore, the practical integrator is shown in the figure, that is RF is connected across the feedback resistor. Thus, RF limits the low frequency gain and hence minimize the variations in the output. Here you can see the circuit for a normal integrator and then practical integrator. Right. In normal integrator, that is called as idle integrator, we are not using any resistors in parallel with the capacitor CF. So in order to maintain the control at the output variations, we have to insert an RF at the practical integrator. Next one is the frequency response of an integrator is shown in the circuits, that is F is equal to 1 by 2 pi R1 CF. Both the stability and low frequency can be corrected by addition of the resistor RF. So roll off means signal will be rolled off when the output you are getting. So you have to get the gain as the maximum for any amplifier. Always the gain must be unity for an operational amplifier. So you have to maintain RF by R1, which is to be constant. And the next one is, we are going to see about differentiator. In that differentiator, we are having a circuit, that is capacitor series, which is connected to the input, and the resistor is connected as a feedback circuit. So here we are having two voltages. One is two frequencies, FB equal to 1 by 2 pi R1 C1, that is equal to 1 by 2 pi R1 CF. The circuit is given below. So here directly we went to practical integrator. So in practical integrator we use R1 C1 in series with RF CF. So RF CF is shunt to the op amp, that is used as a feedback, and R1 C1 which is in series with the input and the inverting inputs. Here also we are going to use inverting input as the input for the differentiator. So differentiator is used as an high pass filter, right? So the figure shows that there is a roll off in the frequency versus the gain. So the gain is in vertical, that is in vertical, and frequency will be in horizontal. If I take the two frequencies FA and FB, I can calculate the FC, which is nothing but the unit gain. So FA equal to 1 by 2 pi R of C1 and FB is equal to 1 by 2 pi R1 CF, that is equal to 1 by 2 pi R of CF. That is, we have to assume R1 C1 equal to R of CF, where FC is unit gain, which is bandwidth for unit gain, bandwidth FC. And since IB equal to 0, IC equal to IF, so we can able to get V out is equal to minus R of C1 dV in by dt. That is the output voltage for the differentiator. So Fs is the frequency at which the gain of 0 dB and it is given by Fs equal to Fa, that is equal to 1 by 2 pi R1 C1. Both the stability and the high frequency noise problem can be corrected by the addition of two components R1 and CF. So R1 CF will predict the values of the output based on the selection of RF and R1 and CF. We can able to get the output without any roll off. And then here you can see the gain of the circuit RF by XC1 increases with the increase in the frequency at a rate of 20 dB by decay. This makes the circuit unstable. Also, the input impedance XC decreases with the increase in frequency, which makes the circuit very susceptible to high frequency noise. When amplified, this noise can be completely override the differential output signal, so we can able to get the output signal without any distortion. So similarly, you can give the input of sine wave and you will get a square wave, and if you give the input of sine wave, we get the spikes at the output of differentiator. So you can compare a sine wave, then output of square wave, and you can compare the square wave and the output of spikes. So differentiator can be used as a high pass filter. So steps for design of practical integrator. First, you have to select Fa is equal to highest frequency of the input signal to be differentiated. Then assuming the values of C1 is less than 1 microfarad, calculate the value of RF. So while doing the practical lab, you can use the same circuit what we studied in our theory. With that, we can able to understand how a differentiator works and how an integrator works. Step 2, you can choose FP equal 20 FA and calculate the values of R1 and CF. So you can get R1 C1 is equal to RF CF. The differentiator is most commonly used in wave shaping circuit to detect high frequency component in the input signal, and a problem is given. Design a differentiator to differentiate the input signal that varies in frequency from 10 Hz to 1 kHz. If a sine wave of 1 volt peak to peak at 1000 Hz is applied to differentiator of part A, draw its output waveform. So with the calculation of Fa and Fb, I can able to calculate the value of resistor by considering C1 as 0.1 microfarad or 0.01 or 1 microfarad. You can take any three values with the values of capacitors not given. So here let us assume C1 equal to 0.1 microfarad and I calculate the values of RF. So with the values of RF, I can able to calculate for Fa and Fb, and finally I can able to calculate the output voltage of an differentiator and can able to plot the waveform of the differentiator for giving the input as well as the output. So if the input is a square wave output, that is triangular output, the output will be in square wave. So at the end of the session, we came to know the comparison between the integrator and differentiator. So in the first session itself, I have told, before starting the session, I have told that integrator is corresponds to low pass filter and differentiator corresponds to high pass filter. So the process of integration involves the accumulation of the signal over time. So you can able to get the accumulation of signal. You can accumulate the signal for a particular interval of time, and hence when there is a sudden change in the signal gets suppressed. So you can get a smoothing of signal by using an integrator. That's why I am calling it as low pass filtering. So low pass filtering is nothing but low frequencies are passed and high frequencies are attenuated. That is, we are having a center frequency Fc. For example, if I take the low frequency as 0 and high frequency as F means, so low pass filter passes only the frequency between 0 to Fc and attenuate the frequency from Fc to F. That is called as low pass filter. So the reverse process of the low pass will be your high pass filter that can be obtained by using a differentiator. So when there is sudden changes in the input signal, we can able to identify the changes by slowly varying the signals are suppressed by the differentiator. That's why we call this as an high pass filter. So low frequencies are suppressed and high frequencies are passed at the output. We call that as a differentiator. Thank you.